Have you ever caught yourself imagining what it would be like to go back in time? Maybe to undo a poorly chosen word, relive a lost embrace, or simply witness the world as it crawled through its early days in history. This isn't a new fantasy. Ever since humanity learned to count time, we've also dreamed of defying it. Time travel might just be the final wish of a restless mind, faced with the fleeting nature of existence. Time slips through our fingers, and in the attempt to hold it still, we've created myths, science, machines, and stories. But why does this idea pull us in so strongly, even if it seems impossible? In ancient Greece, people spoke of Chronos and Kairos, the devouring time and the opportune moment. In many mythologies, there are portals that lead to the past or to the beyond, where the dead reside eternally. Hinduism speaks of infinite temporal cycles, where past and future reflect each other like mirrors on a cosmic river. In this view, time isn't linear, it's circular. And curiously, that same idea is resurfacing in modern physics, where the so-called timeline is not as rigid as once believed. In the 19th century, with the rise of science and the popularity of speculative novels, the idea of time travel gained a new literary shape. H.G. Wells, in The Time Machine, 1895, introduced the modern concept of a technology capable of sending someone forward or backward through time. Fiction opened the doors of imagination, but decades later, physics would suggest that maybe, just maybe, it wasn't entirely a dream. In 1905, Albert Einstein published the special theory of relativity, forever changing our view of time and space. For Einstein, time wasn't absolute. It could slow down, stretch, bend. Physicist Carlo Rovelli, in his book, The Order of Time, 2017, argues that time as we perceive it is a subjective construction. The past and the future exist only in our minds. Modern physics does not distinguish them as absolute entities. This explains why, in experiments with subatomic particles at accelerators like CERN, scientists observed that time can indeed pass at different speeds depending on gravity and motion. But this obsession isn't just rational, it's visceral. Psychology suggests that we are biologically programmed to perceive time as a line. According to psychologist Philip Zimbardo, author of The Time Paradox, 2008, our relationship with time directly affects our emotions, decisions, and even our well-being. People focused on positive past memories tend to be happier. Those stuck in negative pasts or anxious about the future suffer more from anxiety and depression. So, the desire to travel through time may also be an unconscious attempt at emotional repair. It's no coincidence that most time travel stories are soaked in guilt, longing, or hope. In films, we see characters trying to save loved ones, stop wars, reclaim lost moments. Time seems like a cruel judge, but maybe, just maybe, it could be persuaded to rewrite the sentence. This emotional core is evident in works like Interstellar, 2014, which, despite its scientific complexity, is above all a story about love that transcends time. Nobel Prize-winning physicist Kip Thorne, who consulted on the film, once said that the laws of relativity do allow for theoretical time travel scenarios, although they remain beyond our technological reach. There's something almost sacred in this pursuit. We long to travel through time to understand who we were, who we are, who we might have been. Memory is a primitive form of time travel, but limited. Dreams can catapult us into alternate realities, but without control. Science, however, still tries to answer, will we ever control this journey? Is it possible to build a bridge between yesterday and tomorrow? Or are we doomed to walk only forward? The truth is, even in the face of scientific skepticism, the idea persists, resists, and even blossoms. Because deep down, our obsession with time isn't about clocks, equations, or spaceships. It's about humanity's oldest desire, not to let life slip by without meaning. When we wish to go back, leap forward, or freeze time, what we truly long for is to preserve what we love, mend what hurt us, and relive what has passed, or what has yet to come. Close your eyes for a moment, and try to feel time passing. There's no scent, no color, no sound, and yet it's there, invisible, tireless, continuous. With every second, something dies, something is born, something transforms. Time seems to carry us like a silent river, and yet, no one has ever seen it. So what is time, really? A real force that drives the universe, or just an invention of the human mind trying to organize the chaos around us? For centuries, philosophers and scientists have struggled to unravel this enigma. Augustine of Hippo, one of the first to contemplate this mystery, wrote in the 5th century, "If no one asks me what time is, I know. But if I try to explain it, I no longer know." And that confusion still lingers. In our lives, we feel time as an arrow, moving from past to future. But according to modern physics, this linearity might not exist outside the human mind. The traditional notion of time began to crumble with Albert Einstein, who proposed in 1905 that time and space were part of the same entity, space-time. In his special theory of relativity, he demonstrated that time is not absolute, it is relative. This means time can actually slow down for someone moving at extremely high speeds, a phenomenon known as a time dilation. In experiments with atomic clocks placed on airplanes and satellites, such as those in the GPS project, scientists confirmed that time does pass differently depending on speed and gravity. Time, therefore, is not universal. It is flexible, shaped by the forces of the cosmos. But Einstein went even further. In his general theory of relativity, published in 1915, he showed that gravity is not just a force. It is a curvature in space-time caused by the mass of celestial bodies. This means that planets, stars, and black holes don't just exist within time, they shape it. The greater the gravity, the slower time flows around it. This was confirmed in 2010, when scientists compared two atomic clocks separated by only 33 centimeters in height. The one closer to the ground, and therefore subject to slightly greater gravity, recorded time passing more slowly. These discoveries revolutionized our understanding of the universe, but also raised an even more disturbing question. Does time really flow as we believe? Some scientists say no. Physicist Julian Barber, for example, argues that time doesn't exist as a fundamental entity. In his book, The End of Time, 1999, Barber proposes that what we call past and future are merely different configurations of the universe, all existing simultaneously, like frozen frames in a film. What gives the illusion of movement is our consciousness flipping from one frame to another, like turning pages in an album. This idea echoes the a block universe interpretation, supported by physicists like Brian Greene and Sean Carroll. According to this interpretation, past, present, and future all exist equally. There is nothing special about now. The feeling of the present is just a limited perspective of the human mind, a point of observation within infinite space-time events. Like an ant walking along a rope, we only see the spot we're on, but the whole rope is already there. And if time is a dimension like the others, like height, width, and depth, perhaps it can be navigated. But unlike the others, we can't move through it freely. We're stuck, always moving forward, never backward. Why? The answer may lie in the second law of thermodynamics, which says that entropy, or disorder, always increases. Simply put, systems tend to become more disorganized over time. A glass shatters, but doesn't reassemble. An egg cooks, but doesn't return to its raw state. This growth of entropy creates a time arrow, giving us the feeling that time only moves in one direction. However, at the microscopic level, the laws of physics don't require a direction for time. The equations work just as well in reverse. It's only when we look at complex systems, like an expanding universe, that we see this arrow, which leads to a provocative thought. If we could manipulate the initial conditions of a system, could we reverse its entropy, and with it, the flow of time? This speculation remains theoretical, but it raises profound philosophical questions. Is time an objective reality, or a mirror of the mind trying to make sense of motion? Is it an invisible prison, or merely a narrow window into what we can perceive? Neuroscientist David Eagleman says, "The brain doesn't record time, it constructs it." In perception experiments, it has been shown that during moments of fear, trauma, or intense pleasure, our sense of time expands or slows down. This suggests that psychological time, the time we feel, can differ dramatically from physical time. So if time isn't absolute, if it can be stretched, compressed, or even fabricated by the mind, what does that say about our existence? Perhaps the real question isn't what time is, but what it says about us. Because maybe time isn't a line, but a mirror. And in that mirror, we reflect our fears, our longings, our hopes, and everything we wish we could live once more. It was the year 1905. While the world was still recovering from the echoes of the 19th century, learning to live with electric lights and the first automobiles, a young office clerk named Albert Einstein published a series of papers that would forever change the way we understand reality. In what came to be known as the miracle year of science, he introduced the special theory of relativity, challenging what had long been held as an unquestionable truth. The idea that time was absolute, constant, and the same for everyone. Einstein showed that time is relative. It depends on how fast you're moving and the gravitational field around you. In other words, two clocks, perfectly synchronized, can show different times if one of them is traveling very fast or is in a strong gravitational field. And this isn't just theory. In 1971, an experiment known as Haffel-Keating proved it. Two atomic clocks were flown around the world aboard commercial planes, and when they returned, they were slightly out of sync with identical clocks that had remained on the ground. Time had passed differently for them. This is what we call time dilation. When an object moves at speeds close to the speed of light, like a hypothetical spaceship, time slows down for those aboard compared to those remaining on Earth. Practically speaking, this means an astronaut could travel for 5 years and return to find that centuries had passed on Earth. This idea was dramatically portrayed in the film Interstellar, 2014, when the characters spend a few hours on a planet near a black hole, only to return to the spaceship and discover that decades had gone by. The origin of this effect lies in the most famous equation in modern science, E = U. It shows that mass and energy are interchangeable, and that the universe is woven from the interplay of space, time, and motion. But it was in 1915, with the general theory of relativity, that Einstein took his boldest step. He proposed that time is not just a coordinate running alongside space, it is part of a four-dimensional fabric called Kein space-time, which can be bent, twisted, and distorted by the presence of mass. Imagine a trampoline. If you place a bowling ball at its center, the fabric dips. Now if you roll a marble across the edge, it won't travel in a straight line. It will curve toward the heavier object. That's how gravity works in Einstein's model. Planets orbit the sun, not because they're pulled by an invisible force, as Newton suggested, but because they follow the natural path in a space-time curved by the sun's mass. And time, in this analogy, also dips. Where there is more mass, there is more curvature, and where there is more curvature, time slows down. This phenomenon becomes especially extreme in black holes, regions of space so dense that nothing escapes their gravity, not even light. Near them, time nearly stops. In theory, an observer falling toward a black hole's event horizon would experience time so dilated that from Earth's perspective, they'd appear frozen. Stephen Hawking, one of the greatest black hole researchers, said that, around them, the known laws of physics reach their limits, and with that, possibilities once deemed impossible begin to emerge, including those about time. And this is where one of the most fascinating ideas in modern physics arises: wormholes, also known as Einstein-Rosen bridges. These hypothetical structures would be shortcuts through space-time, capable of connecting not only distant places, but different moments in time. Imagine a sheet of paper. If you mark two dots, they seem far apart. But if you fold the paper, they can touch. That's the idea behind wormholes, bending space-time. In the 1980s, physicists Kip Thorne and Michael Morris demonstrated mathematically that these tunnels could exist, if stabilized by a form of exotic matter, something we have yet to confirm exists. According to Thorne, time travel may be possible within the laws of physics, but the technological and energetic demands are so absurdly high that it remains unfeasible with current knowledge. But perhaps the most interesting part isn't the physical journey itself, it's what it represents. Einstein's relativity didn't just give us tools to imagine such a crossing. It gave us something deeper, the notion that time is not a line, but a landscape. and every point in that landscape, every moment of past, present, and future, and exists. They don't vanish. They don't stop being. They simply hide behind the curvature of reality. If that's true, then maybe time doesn't carry us anywhere. Maybe it's all already there, waiting. And we, as travelers with limited awareness, merely cross through it like someone strolling through a field of memories, touching one moment at a time. Relativity showed us that the doors of time exist, but perhaps they aren't outside. Maybe they're within. And to open them, we don't need a warp drive, just a question we haven't yet asked. Imagine you discover a way to travel back in time. You decide to visit a distant past, decades before your birth. At first, everything feels fascinating, until you make a mistake. Somewhere during the journey, you accidentally prevent your grandparents from ever meeting, or worse, you cause, directly or indirectly, your grandfather's death before he has children. So, what happens now? If he never had children, your father was never born. And if your father was never born, then neither were you. But if you never existed, how could you have traveled back in time to prevent that meeting? This is the famous and unsettling grandfather paradox, first formulated in the 1930s, and it remains one of the strongest logical barriers against the idea of time travel to the past. The contradiction seems clear and unavoidable. An action in the past negates your own future existence. But can the universe really allow such a logical breakdown? Or is there something within its structure that subtly, or absolutely, prevents these paradoxes from happening? To seek answers, science began exploring mathematical and physical models that could bypass or explain time paradoxes. One of the best-known attempts came from physicist Igor Novikov, who proposed the Wecht principle of self-consistency in the 1980s. This principle states that any action taken by a time traveler is already part of the universe's history. In other words, even if you travel to the past, your actions cannot alter what has already happened, because they already happened and were always part of the timeline that led to the present, This concept is explored in films like 12 Monkeys, 1995, where the protagonist tries to prevent a global catastrophe, only to discover that his efforts are, ironically, a necessary part of the chain of events that caused the disaster. In this view, paradoxes don't occur because the past is resilient, flexible in appearance, but unchangeable in essence. But things get even more complex when we enter the realm of the butterfly effect, an idea from Parmenides chaos theory, popularized by meteorologist Edward Lorenz in the 1960s. Lorenz demonstrated that highly complex systems like weather are incredibly sensitive to initial conditions. A tiny change, like the flap of a butterfly's wings in Brazil, could theoretically trigger a hurricane in Texas weeks later. Applied to time travel, the butterfly effect suggests that even the smallest intervention can have catastrophic and unpredictable consequences for the future. A wrong step, an innocent gesture, a poorly chosen word, and everything changes. Simply being present in a time that isn't yours could be enough to rearrange history entirely, whether you notice it or not. As fascinating as it is, this idea raises deep ethical and existential questions. What if we went back and stopped wars, epidemics, tragedies? Would we be saving the world, or destroying the very path that led to our existence? How many lives emerged? How many cures were discovered? How many minds awakened precisely because of the suffering we'd wish to erase? Some scientists have tried to resolve the paradoxes with the hypothesis of parallel universes, inspired by the how many worlds interpretation of quantum mechanics, proposed by Hugh Everett in 1957. According to this view, when you travel to the past and change something, you don't alter your original timeline. You simply create a new divergent timeline, a parallel universe where the change occurred. Your original reality remains intact, but now you exist in a newly branched version of reality. This concept is hard to test, but it's not mere science fiction. In theoretical physics, especially in inflationary cosmology and string theory, the idea of multiple universes is taken seriously by many scientists. Physicist Max Tegmark, for instance, classifies multiverses into 4 levels and considers in level 3 exactly this possibility, that every choice, every quantum event, spawns a new universe with a different outcome. In that sense, time travel would be like jumping between branches of an infinite cosmic tree. Still, something remains deeply troubling. If the past can be changed, even in another universe, what happens to memory? What happens to belonging? Who are we if we undo everything that shaped us? These questions escape the realm of physics and dive into philosophy. Perhaps that's why, despite all the models, paradoxes, and theories, time travel remains wrapped in mystery. Because it's not just a scientific issue, it's an existential one. Do we want to go back to fix something? To understand it? To relive it? Or just to ease the ache for what will never return? In the end, paradoxes are not just logical errors. They are mirrors that reflect our most intimate conflicts. The desire to change the past clashes with the fear of losing the present. And perhaps, deep down, the greatest paradox is this: wanting to alter time without changing anything inside ourselves. Imagine the universe as a vast cosmic tapestry, woven with stars, galaxies, and gravitational fields. A fabric that stretches in every direction, rippling with the presence of matter and curving under the force of gravity. Now, imagine that instead of walking along the surface of this tapestry, you could fold it and bring two distant points together with a simple touch, as if a hidden road opened between two worlds, or two times. This is the essence of what we call a wormhole, one of the most intriguing and speculative concepts in theoretical physics. The name may sound fanciful, even childish, but the idea is firmly rooted in the equations of general relativity. In 1935, Albert Einstein and his colleague Nathan Rosen described a mathematical solution to Einstein's gravitational field equations, known as the Einstein-Rosen bridge. It represented a connection between two separate points in space-time, like two mouths joined by an invisible tunnel. In theory, this tunnel could span the cosmos, or even link different moments in time. But the predicted wormhole would be inherently unstable. It would appear and collapse within a tiny fraction of a second, far too quickly for anything to pass through. To keep such a passage open, we would need a form of matter we don't yet know, the so-called exotic matter, with negative energy and anti-gravitational properties. We don't know if such matter truly exists, but the idea has theoretical support. In 1988, physicists Kip Thorne, Michael Morris, and Ulvi Yurtseva published a paper showing mathematically that stable wormholes could, in theory, allow time travel, as long as they contained this exotic form of energy. Kip Thorne himself, who later won the Nobel Prize in Physics in 2017, served as the scientific advisor for the film Interstellar. In the movie, a spacecraft enters a wormhole near Saturn and emerges in another galaxy. The visual representation was based on real calculations. And while the plot includes fictional elements, its scientific foundation is plausible, though, for now, far beyond our technological reach. Mathematically, it's possible. Engineering says, not yet. But as history often shows us, what is science fiction today can become reality tomorrow. In 1903, powered flight was a physical impossibility. By 1969, humans were walking on the moon. The progress of knowledge does not obey the limits of the impossible. It crosses them, one equation at a time. Yet wormholes raise not only physical questions, but also moral, philosophical, and ontological ones. If they were real, who would have the right to use them? What purpose would they serve? Escape routes from death? Gateways to rewrite the past? Windows to peek into the future? Or perhaps instruments of wisdom, meant to teach us that time is not something to conquer, but to understand? And then there are the risks. The slightest miscalculation, the smallest gravitational instability, and the journey could become a trap with no return. According to studies by physicist Matt Visser, an expert in space-time geometry, any traversable wormhole would need shielding from radiation, internal collapses, and quantum disturbances that could destroy the tunnel in unpredictable ways. In other words, even if we could create them, we might never be able to control them. And there's another possibility, even more provocative. What if wormholes aren't built, but discovered? Some scientists suggest that such structures might already exist, hidden within the cosmos, invisible to our eyes, connecting distant regions of the galaxy, or even parallel universes. In 2016, a team of researchers at the Institute of Astrophysics of the Canary Islands published a study speculating whether certain gravitational anomalies observed in galaxy clusters could be signs of such structures. The hypothesis is still controversial, but it has not been ruled out. And even if we never travel through one, the existence of wormholes radically changes our understanding of space and time, because they suggest that the universe may contain shortcuts, that time is not a linear prison, but a curved, entangled, and perhaps navigable field. It's as if the cosmos were whispering, "The path you see is not the only path that exists. There are tunnels hidden among the stars. Doors locked by laws we have yet to understand. And maybe, someday, someone will find them. Maybe that someone will be a future version of ourselves, looking back, trying to say, there was always another way." When we hear the term time travel, we almost always think of going to the past, undoing mistakes, meeting loved ones again, reliving moments that slipped away. But what about the future? Is it possible to move forward in time, not as an abstract idea, but as a physical, measurable, observable reality? The answer, surprisingly, is yes. Within the limits of current science, traveling into the future is not only possible, it has already been done. Not in the spectacular way imagined in movies, with spaceships leaping through portals, but in a subtle, almost imperceptible way, and absolutely real. The key lies in Einstein's equations, and in what they reveal about the elastic nature of time. The theory of relativity showed us that time does not pass at the same rate for everyone. It depends on two main factors: the speed at which we move and the strength of the gravitational field around us. This phenomenon is known as time dilation, and it has been confirmed many times. One of the most famous tests was the High-Huffle-Keating experiment, conducted in 1971. 4 highly precise atomic clocks were flown on commercial airplanes traveling around the world in opposite directions. When they returned and were compared to identical clocks that had remained on the ground, they were slightly out of sync, a small difference, but one that was predicted and confirmed by relativity. Time had passed more slowly for the moving clocks. And here's the most fascinating part. This happens all the time. GPS satellites, for instance, must constantly correct their clocks because they orbit the Earth at high speed and in a different gravitational environment. Without these corrections, their location calculations would drift by meters each day. This means that every time we use GPS, we are interacting with technology based on the understanding that time is relative. But the most extreme effects occur at speeds near the speed of light. In laboratories like CERN in Switzerland, subatomic particles called muons are accelerated to 99.99% the speed of light. Normally, these particles have a lifespan of just microseconds. However, when accelerated, they live far longer than expected, because for them, time slows down. In other words, they are traveling into the future, while time on Earth moves forward as usual. The idea that the faster you move, the slower time passes for you, is central to modern physics. It means that if a spacecraft could reach near light speeds, its crew could travel for, say, 10 years, and return to Earth to find that centuries had passed here. Scientists call this a one-way trip to the future, and technically, it doesn't break any laws of physics. The challenge, of course, is technological. We would need absurd amounts of energy, shielding from cosmic radiation, and materials capable of withstanding the forces involved at such speeds. But there's another path: extreme gravity. Remember, time moves more slowly in stronger gravitational fields. This means that near a black hole, where gravity peaks, time nearly stops. In the film Interstellar, this idea is portrayed with scientific accuracy. A planet orbiting close to a black hole experiences time so dilated that 1 hour there equals 7 years on Earth. This comes directly from Einstein's equations. And while we haven't sent probes to such regions yet, the implications are real. And when we think about humans, there are subtler, but no less striking, examples. Russian cosmonaut Sergei Avdeyev, after spending a total of 747 days in orbit, experienced a small amount of time dilation. He aged about 0.02 seconds less than us. It may seem tiny, but it's a legitimate form of time travel, forward, even if on a microscopic scale. These examples show us something extraordinary. It's no longer a question of whether time travel to the future is possible. It's only a matter of scale. We already live in a universe where time can be manipulated, stretched, and slowed, where, depending on where we are and how we move, the future can be reached faster. So what does this mean for us, here and now? Perhaps it means the future is not a distant place, but a direction we can choose and even accelerate toward. Maybe not with machines, but with decisions, with awareness, with science. Perhaps every choice, every well-lived second is a subtle form of traveling toward a different tomorrow. Because in truth, the future has always been there. It was just waiting for us to arrive. In a quiet corner of the internet, where forgotten forums and long-deleted archives still linger, lives one of the strangest and most fascinating chapters of humanity's obsession with time, the chrononauts. People who claim, with conviction and detail, that they have already traveled to the past or future. Some describe their experiences with such precision that they evoke fascination, skepticism, and sometimes fear. But who are they? And why do these stories, however improbable, continue to captivate our imagination? The most famous case emerged in the early 2000s on a discussion forum called the Time Travel Institute. An anonymous user, under the pseudonym John Titor, began posting messages claiming to be an American soldier from the year 2036. His mission? To travel back in time to retrieve an IBM 5100 computer allegedly needed to decode legacy systems and prevent a future collapse of civilization. Titor's messages included technical descriptions of the time machine based on general relativity and dark predictions about a coming civil war in the United States. For months, Titor answered questions, detailed his equipment, and even published diagrams and calculations that, according to him, supported his story. His posts mentioned micro-singularities, gravitational distortions, and shifts in time axes. And even though many of his predictions, like a global war in 2015, never came true, his story remains one of the most analyzed phenomena in internet culture. Books have been written, documentaries produced, and even physicists like Michio Kaku have been asked publicly about the plausibility of the concepts he described. But John Titor is not alone. On sites like Reddit, Quora, and obscure forums, reports frequently emerge from people who claim to have had inexplicable temporal experiences. Some describe reality slips, moments lived out of sequence. Others report déjà vu so intense and precise that they begin to question the linearity of time. There are even those who claim to have been abducted and shown visions of the distant future on projected screens hovering in mid-air. These accounts multiply, often accompanied by dates, coordinates, distorted photographs, or supposedly erased files. Most can be explained as hoaxes, imaginative fabrications, or even neurological phenomena like cryptomnesia, where the brain creates false memories from forgotten information. Yet even the most rigorous skeptics admit something intriguing: the symbolic consistency of these stories. Many of them share the same archetypes, the same fears and hopes, the same metaphors of loss, return, and redemption. Some behavioral scientists believe these stories are not lies, but unconscious ways of processing trauma, anxiety, or deep desires. The idea of going back to fix something, or glimpsing the future to find meaning. In this context, time becomes not just a physical dimension, but a psychological territory, and the chrononauts, travelers of the self. Yet not all reports remain confined to internet fiction. In 2003, a team from the University of Connecticut conducted a systematic analysis of testimonies involving anomalous temporal experiences. Their conclusion was that while no physical evidence was found, the subjective experiences were so vivid and coherent that they warranted closer study by psychology and neuroscience. The human brain, after all, is capable of generating complete realities, including those involving time. Still, some stories defy even scientific interpretation. like that of the alleged time traveler, Andrew Carlson, who was reportedly arrested in 2002 after making millions on the stock market with investments deemed impossible to predict. According to rumors, he confessed to being from the year 2256. While the story likely originated as satire in Weekly World News, it continues to circulate through videos, articles, and conspiracy forums to this day. And what about the mysterious photos? Like the famous 1941 image showing a man wearing sunglasses, modern clothes, and holding what looks like a digital camera in the middle of a 1940s crowd, or videos where people appear to be using cell phones in eras where such technology didn't yet exist. Most of these have been debunked, explained as perspective errors, coincidences, or digital edits. But the truth is, we want to believe. We want time not to be a rigid track, but a map with hidden routes. Perhaps that's the role of bizarre theories, to feed our imagination where science has not yet arrived. Because even among equations, labs, and telescopes, there is still room for mystery. And while science builds the tracks of what is possible, fiction keeps alive the fire of what might still be. In the end, chrononauts are more than just characters in improbable tales. They are our symbols of our ancestral desire to recover what was lost and discover what lies ahead. And even if they never prove their journeys, they keep traveling, within us, in the folds of curiosity, in the orbit of hope. Close your eyes for a moment and try to remember the scent of your childhood home, or the sound of a laugh that marked your youth, maybe the image of someone who's gone, maybe a moment of silence that never returned. If you manage to relive any of it, even for just a second, then you've already traveled through time, because memory, that invisible force living in every corner of our brain, is of the deepest and most real form of time travel we know. Science has long tried to understand how we store, access, and relive memories. What we know is that they are not static files, stored neatly on a shelf in the brain. They are active reconstructions. Each time we remember something, we rebuild that memory, drawing from sensory, emotional, and cognitive fragments. It's as if every memory is a portal, and the act of remembering, a crossing. According to neuroscientist Joseph Ledoux from the Center for Neural Science at New York University, emotional memories are the most vivid and enduring because they activate deep structures like the amygdala and hippocampus, areas responsible for encoding events essential to survival. That's why we remember moments of fear, pain, or love with such clarity, even if we've forgotten what we ate yesterday. But perhaps the most fascinating truth is this: the brain doesn't clearly distinguish between remembering and imagining. Neuroimaging studies, like those led by Daniel Schachter at Harvard, show that when we recall the past or project into the future, we activate the same neural circuits. In other words, remembering is a form of rehearsal. Imagining the future is a way of repeating the past. And what we call the present is just a brief point of contact between these two forces, memory and projection. That's why many researchers, including psychologist Endel Tulving, describe episodic memory, the kind linked to personal experience, as a form of mental time travel. When we access autobiographical memories, we transport ourselves to that moment. We feel it again. We relive it. Our body reacts. Heart rate changes. Breathing shifts. Pupils dilate. Because the brain doesn't just remember, it relives. And this journey doesn't need to go backward. We can travel to what hasn't happened yet. Philosopher Martin Heidegger called this being projected. For him, the human being is essentially a creature thrown toward the future. We live constantly oriented by what is yet to come. Dreams, plans, fears, expectations, all of it pulls us into a time that hasn't yet arrived. A time with no face, but already with shape. In this sense, every time we close our eyes to imagine a different future, we are creating a possible reality. A timeline that exists only within us, but that can become real through the choices we make today. The present, then, is the intersection where the past meets what is yet to be. And there's another dimension, the time of consciousness. In altered states of perception, like deep meditation, hypnosis, the use of psychedelics or near-death experiences, time can expand or disappear. People who've experienced these states often report sensations of eternity in seconds or entire lifetimes lived in moments. A study led by Dr. Rick Strassman at the University of New Mexico, involving patients under the effects of DMT, revealed that many participants felt they had stepped outside of time and existed beyond the temporal line. These accounts are hard to measure, but they can't be ignored. They point to a deeper mystery. Is time truly external, or is it a product of our consciousness? If we expand the mind, can we access layers of reality where time doesn't flow, but pulses? And so comes the inevitable question: if we could control our memories, and with them, our sense of time, would we still need machines to travel? Or would it be enough to learn how to dive deeper into ourselves? Perhaps we'll never build a time machine with gears and buttons, but every dream, every memory, every deep meditation are invisible engines that carry us. Perhaps the greatest time travel isn't into the past of books or the future of calculations, but into the abysses and peaks that live within the mind. Because in the end, it's inside us where time truly lives. There is a hidden world beneath everything we see, a world that doesn't follow the same rules as our everyday lives. In this world, particles can exist in two places at once. They can pass through solid barriers, influence other particles light years away, instantly. A world where time, causality, and logic, everything we think we understand, dissolves into mist. This world is called quantum mechanics, and perhaps within it lies the strangest and most promising key to time travel. Quantum mechanics studies the behavior of matter and energy on subatomic scales. And unlike classical physics, where events are predictable and deterministic, the quantum universe is probabilistic, fluid, and astonishing. Simply observing something changes how it behaves. Reality seems to be shaped not only by matter, but by the consciousness that perceives it. One of the most iconic and unsettling experiments is the double-slit experiment. First performed by Thomas Young in the 19th century, then reinterpreted in quantum terms during the 20th. In it, particles like electrons are fired at a barrier with two slits. Logically, they should pass through one slit like little bullets. But when unobserved, they behave like waves, passing through both slits simultaneously and interfering with themselves. When measured, their behavior changes. They act like ordinary particles, choosing just one slit, as if reality only decides what it is when someone is looking. This phenomenon, known as quantum superposition, suggests that particles exist in multiple states simultaneously and only collapse into a concrete reality at the moment of observation. It's as if, before we choose, all paths exist at once. In 1957, physicist Hugh Everett III took this idea to its extreme. In his many worlds interpretation, he proposed that the universe doesn't collapse into a single reality when a choice is made. Instead, every possible outcome happens, but in different universes. If you flip a coin, there's a universe where it lands heads, and one where it lands tails. One where you caught the train, another where you missed it. One where you said yes, another where you said no. At every decision point, the universe branches infinitely, creating parallel realities that coexist, unseen. This is where modern physics begins to touch science fiction, and vice versa. Because if these multiple universes exist, could we access them? And if so, wouldn't that be, in some way, a form of time travel? Some scientists suggest the answer is yes. Physicist David Deutsch from the University of Oxford believes that quantum mechanics could allow time travel without paradoxes, precisely because of the existence of these many worlds. If you go back in time and change something, you don't alter your original timeline, you simply create a new one. Thus, the grandfather paradox disappears. You can prevent his birth in one timeline without affecting the one from which you came. And these aren't just theories. In 2014, researchers at Griffith University in Australia developed a computational model of quantum simulations that recreated effects similar to time travel through feedback loops in quantum circuits. The experiment is still far from practical application, but it shows that, mathematically, time can be bent, simulated, and even reversed under certain conditions. There's also the phenomenon of quantum entanglement. When two particles are entangled, the state of one instantly affects the state of the other, no matter how far apart they are. Einstein called this spooky action at a distance, because it appears to violate the speed of light. Today we know entanglement is real, and it has been confirmed in experiments awarded with the Nobel Prize. But what does it say about time? If two particles can talk across space, could they also exchange information across time? And what if these invisible connections exist between different realities? What if in dreams, in intuitions, in déjà vus, we are touching, for a brief moment, alternate versions of ourselves? Not as a metaphor, but as a whisper from the multiverse, an echo of who we also are, somewhere else. Quantum mechanics doesn't prove that time travel is possible, but it doesn't deny it either. On the contrary, it opens doors that classical physics would never allow. It tells us that reality is bigger than we can perceive, that time is not a straight road, but a web of interwoven possibilities, and that perhaps the timeline we're in is just one among trillions. In the end, what quantum physics offers us is not a final answer. It is something even more powerful, the freedom to imagine. And in a universe where everything is possible until observed, who can truly say where now ends and infinity begins? If today, right now, you had the chance to go back in time, where would you go? What moment from your life would you choose to touch with your own hands? To whom would you say what you left unsaid? What gesture would you try to undo? Or what hug would you try to hold on to just 1 second longer? It seems like a simple question, but it carries the entire weight of human existence. Because this isn't about science, it isn't about physics, it's about the heart, about guilt, about regret, about the things that, even as the years pass, still live inside us, like a knot in time. Throughout history, countless cultures have dreamed of rewriting the past. The Greeks spoke of the Moirai, the weavers of fate who spun the thread of time. Hindus saw time as cyclical, where all things return. Christianity brought the idea of repentance as a spiritual way of correcting what was done. And modern science, even with all its precision, still looks at time with reverence, as a phenomenon that defines everything, yet remains beyond our full understanding. Physics may say that time is relative. Philosophy may say that time is a mental construct, but we know that time is something more. It's what separates presence from absence, a voice from silence, pain from memory. If we could go back, would we really change anything? According to psychologist Barry Schwartz, author of The Paradox of Choice, more options don't mean more freedom. They mean more anxiety, more doubt, more regret. The idea of choosing again, redoing everything, rewriting life, sounds liberating, but it also carries a wound. The pain of knowing that even with infinite choices, we might still make the wrong one. And if we went back and avoided a mistake, maybe we'd never learn to grow. If we prevented a loss, maybe we'd never understand the value of presence. If we changed one word, perhaps we'd never learn the weight of silence. Neuroscience shows that regret is a complex cognitive function. It activates brain regions tied to memory, empathy, and decision-making. Feeling regret is a way of learning. It's the brain trying to simulate what could have been, so that in the future, we choose better. But there is something that science still cannot measure, what we feel when we remember who we once were. And sometimes, all we want is to return, just to witness, to see that smile again, that old street, that sunny morning we didn't know would be the last. We just want to touch, even from a distance, what time has taken, not to change it, but to say thank you. Because deep down, the greatest power of time travel wouldn't be to rewrite history, but to understand it, to look back with new eyes, to recognize that everything that brought us here, the mistakes, the victories, the silences, were all part of the equation that shaped the present. And maybe that's why we can't physically go back, because our time, in its silent wisdom, pushes us forward. It asks us to live with the marks, to learn from the wounds, to grow with the absences. If one day we do gain the power to move through time, may it not be to erase our stories, but to honor them. May we return to the past not as surgeons of fate, but as travelers of gratitude. And as we gaze toward the future, may we not see it as a question mark, but as an invitation, because true time isn't in clocks, or orbits, or equations. It's in the now, in the moment you breathe, in the instant you hear these words. This is the only time that truly exists, and within it, you can do anything.